Yeah, so this is going to be a little extended demo of a motion profile program that is moving an object to position an object with a sigmoid speed profile, a S-curve speed profile. So we're going to do here is there's going to be, I'm just going to demonstrate the program a little. Something here. So it's pretty much reset. So yes, of course we should look at the screen here. So what's been recorded here is the red here is the velocity set point. We have the acceleration, current jerk, current snap, and on the bottom here is the estimated position. And we are doing automatic scaling here. This is in TI portal with the trace. And here is the instance of this positioning analog sigmoid program. So just to have a little look here is what we can do is start and stop it. This is from the drive, that the drive is enabled. Reset an arrow. I'm going to try to avoid those. And X here is the current speed, or the speed from the drive. External reference is the position I want to go to. External position is where I am. Speed set point, and here is a constant for when to start on this sigmoid curve. It's an exponential, so somewhere you would have to start because it's asymptotic, so it will never reach the min on the maximum. And here are some parameters that we have. We are not going to look at those much, but what we're going to test are some of these functionality switches and also the program mode here. So if we move back to the parameters here, the timeout ready is if we output a ready command to the drive, we expect to get a ready feedback, and if we don't, there's an error. And if we have a velocity from the drive, of course, if the velocity deviates from what I have as a velocity set point, it would be bad and it wouldn't work. On an error like that, we would just try to stop the program. Maximum set point, that's a reference there where to go from our 0 to 100, can be meters, millimeters, or whatever. Gear ratio is that if your set point to the drive has to match, let's say, a velocity in units per second, and ultimately a distance you move. So this, you can look at it as a gear. So what you have to adjust this to is so that a set speed on your drive matches a unit per second and a unit in, let's say, movement or displacement. Program mode is 0 is move absolute, 1 is move relative, 2 is move positive at this speed set point that we have up at 0.5, and 3 is move negative. We're going to look at those. The maximum velocity ILO is 4, whatever it is, units per second. The minimum position velocity is 0.01 units per second. And that's the velocity you have when you're positioning, you're creeping towards your target at this velocity. And then we have some safety margins here. Let's say if we have a really steep deceleration, we can start a little earlier, move to this, let's say, positioning velocity, so we're not running into a wall or overrunning over a target or something like that. And that's dynamic. The 0 here is at 0 deceleration, and the 1 here is at the specified deceleration, which is 0.15 units per square second here. And if it's higher, you will have a higher value than 0.01, and if it's lower, it would be a value between 0.05 and 0.01. You can switch this to 0, whatever, if you don't want to use it. Positioning tolerance is what we're aiming for in units. Acceleration is in units per second square. Deceleration, units per second square. Jerk is units per second cubed. And sampling time is at what rate or frequency is this program executing. Now it's 5 milliseconds. Then with the functionality switch, we're going to look at those, not the first two, they are obvious.
no velocity feedback is the X here. I don't have that, and then I use the set point that I have as my velocity feedback. Equidistant execution is running on interrupt. The program can execute on a non-interrupt, so the execution time can fluctuate, but it should basically run on an interrupt. The program is using the measured time between program execution, so it would work. And the rest, we are going to try to demonstrate those. Output is set point to the drive. This is the speed. And then we can just look at the comments here too. And here is the program state. It stopped. Yeah, there are some states here. If we want to know the states here, we would have to look in the program. And the states are here. Down here, they are just specified as constants. States is positioning stopped, wait for drive ready, accelerating, stop. We're going to demonstrate that. Maximum velocity state, deceleration state, then we just go into stop, and positioning active, that's when we are trying to hit the target. And the position at minimum velocity is that we are sweeping towards the target. And when we add it, the faults that we have here is no fault. Parameter errors, if the program can't live with the parameter you are specifying, you will not be able to run it. You get an error too. Drive enable timeout, you get an error. And then there's, if you have a velocity feedback from the drive and it deviates from what you are setting as a velocity, you get an error and the program just try to abort. You can't live with that. And then we are looking at these modes that we're going to look at: absolute, 0, relative to actual position, set velocity, positive direction, at maximum velocity, or the velocity set point, which is the this one here. Move at set velocity, negative direction, at maximum velocity. It's not this maximum velocity, but the velocity set point. That is what it was. And then you get some more information after. You can do tuning. And what else you have as an output here is the Y3 is estimated distance. This is set point to the drive that's being multiplied by the gear ratio, divided by the gear ratio, whatever. And the D2 is plus and minus if the drive accepts negative set points. Fault information, we looked at those. This one is true as long as there is a fault. The enable output goes to the drive. You expect an XE feedback. Direction, a true is positive direction. A false usually go negative direction. And here, yeah, we can look at. So positioning is active. Positioning aborted, which means that you switch off while you are positioning or running, which means that XH has switched to false. And position is down and conserve position. We are not going to look at those during demonstration. So then we have to do something and try to do something. My trace is running. So what we can do is that we can start. There are no options on here. I'm just going to keep the parameters. Of course, we have to change those. That's what we are going to do first. But first we can do mode 0, move absolute, and I can go to 5, for instance. True. I might reach the 0.5 velocity, or I might not. I do. So now I start to decelerate, and I get an acceleration of 0.2 that is specified, and I get around 0.15 for the negative or the deceleration. It won't be exact, but because here it's being added its minimum velocity to have a smooth landing at the minimum velocity. Here's the jerk, and the jerk specified here. This one is matching 0.2. So I would expect to get 0.123, and this one is not matching. So those are arbitrary. So that was step mode, and now we can do relative movement, which is 1. So what I can do is I can try to move to 7, that will probably be +2 if I'm lucky. Now I can't reach full speed, of course, I'm moving a short distance. The jerk is increasing here, and so on. It keeps the acceleration. That's what it said it should do. And I did position. I spent 1 second in the minimum speed state, and 12 seconds or 13 seconds was my position. And I moved to 7 about. I could probably try to move back. I should hit around 5. I should pretty much reach the same velocity, and these should be equal fairly down here. And I should end up close to 5, I hope. Close enough. Now that was program mode 1. In 2, I'm just going to move in positive direction until I stop. Now I should reach 0.5, and it will move on. It does not crash into the walls. It would decelerate at close to 100. But the thing is, this is just move at a velocity, and you should stop it. And it stops. Yes. So if I select 3, it doesn't care what you have for set point here. 3 is move in negative direction. And if I'm looking here, of course the distance should decrease. And now we can keep running and just check out that it's not running into the wall in a negative direction, or at the end stop, or something like that. Of course, you would have a safety system of some sort here that preventing, let's say, mechanical damage or something. We could try to avoid them in the program too. So now it should stop short of 0 or something. There's no minimum velocity here or anything like that. It just goes to stop and is close to 0. The rest we are going to use smooth absolute because it's easier. Of course, a negative one it would not accept. So what we can do here is now we can try to say this enable moving set point. That we can switch that to true, which means that while the program is running, I can change the set point. I'm going to try to run for 15. Because when I looked at the states, I would need to get in the states 4, a maximum velocity. That's the only position it allows me to change the set point. I can't decrease it, but I can increase it. Now I'm in 4. So I can just try for 10. It uses 10, but if I just keep running, it would run to 15, but it just keeps the internal set. But what you wish for is, now it should accept 20. Then I should pass 15. That was my original one. The 10 it didn't care about. It didn't change that set point at all, but it should run to 20. So I can increase it. But I can't decrease it, because then you would have all sorts of troubles with deceleration and things like that when you allow it. What you can do is that you can allow a decrease down to where you would start to decelerate. Could be done, but here is only an increase. So that was an increase. That was the moving set point. It would work in the other direction too. I'm not going to show you. Now we have this low stop while accelerating. If that one is false, what we can do is we can say, okay, I want to move towards 0. I have to switch it off and on because it's active on the positive edge. So now I can, when I'm in 4, I can stop. You can always stop when I'm at maximum speed because then you get this nice deceleration profile. No positioning whatsoever. So now I'm going to start it again. Now I'm going to just switch off now. And it's accelerating to the full speed. But as soon you can see it, of course you have to switch it off. I didn't do that. It was a poor demonstration. I have to do it one more time. I think. Yeah, now we're done. Program mode 0, done. Here, true, false. Now I hit. Now I can see the program is switched off, but it does the acceleration, but it's not going to enter mode 4 maximum speed. It's just going to decelerate. It's as soon as acceleration is done, we do the deceleration, and just keep the jerks and acceleration and snap here nice and tidy. But there is an option. Of course, it might not be possible to wait for full speed. And then we can say that we can allow a stop while accelerating. So what I'm going to do, I'm going to start and I'm going to stop really quick. I have to do it because there's no long distance here. Start, stop. So what it did was it accelerated a little and then it decelerated too. No, now this is slow. I should probably wait a little longer. But I do. Let it have a little and then I switch off. And you can see here is a jump in acceleration and you get it in jerk too. But the program tries to smooth the curve so you don't just get an abrupt deceleration directly. So it kind of accelerates a little bit before it stops to make it smooth. Of course, there could be an option to say, okay, just go to deceleration and get the jerks that you get there. That's what you get, and the snap you get is the snap you get. But the way it is now, it just tries to smooth this stop while accelerating. Now we have looked at the acceleration parameters, has been using those, and the jerks we get are not what I specified. But what we can do is we can enable enforce jerk parameters. Now we can try to move, for instance, to 10, a little bit longer. This point 1, 2, 3 matches the 0.2, so I would expect to get 0.2 here with this jerk, but it uses the jerk. But let's see what happens when we decelerate here. Deceleration I specified at 0.15, but I say the deceleration jerk should be 0.1, so that's what it should aim for. There's 0.1, and the deceleration, I get what the jerk says it is, so it's not 0.15, it's a little higher when it moved. I can keep this one on, jerk parameters. I'm going to switch it off later on, but now I'm going to try, now I moved the maximum speed, now I'm going to try to move a short distance. I just want to move back to 9. And normally now the jerks, they would increase. And I'm enforcing, say, okay, this is what is allowed. And the acceleration, I get the acceleration I get. And I get the maximum velocity that's possible. And here you see it's a little less than 0.1, and that has to do with this. Let's say the minimum speed is slowly added when I'm decelerating here to get a smooth landing here on the minimum speed. Now we moved 1, didn't we? And I can say out. So I can move back to, I can move to 8. Another step down, off and on. And you can see what happened to the jerk. Oh, that's going to hurt. What it did was I get the acceleration, because that's what's aiming for. 0.2 and 0.15, and the jerk is what I would get. Now, also, if I'm moving larger distance, I'm going to switch this off. So that was short distance. So I can say I want to do 30. Let's do 20. Wait. Switch on. Now you can see the jerks I now get, they are small. Now I get this acceleration or whatever I have, because this my setup matches this 0.5 in speed set. We can wait until it just reaches the position, because it didn't allow the speed to increase. I said the maximum speed you get is this. Now I can get a maximum speed of 0.4 if it is possible. I'm going to move back to 0. What I'm going to do now, I'm going to allow for velocity increase. Say, but not more than 4. I'm not crashing into the wall. Now we can see, moving this distance, if I'm lucky now, I'm going to pass 0.5. I get a higher speed, but it has done a calculation. And what we can see here is the jerk is a lot lower. The acceleration is 0.2, that's what I specified. And it's going to immediately switch to positioning when it reaches, when acceleration is done. The calculation is done like that, and I should get a deceleration of 0.15, wasn't that what I specified? Yes. And so on, and I should hit 0. Now the jerk is lower. Now if I say I want to enforce the jerk parameters, and I move back to, I should get a different speed, but I should get my specified jerk, so 0.123 would correspond to 0.2 in acceleration, because they match closely. 20. Yeah, we can wait until it reaches 20. So now it starts to decelerate. Now it's in state 6, which was positioning. So it's landing smoothly at the minimum velocity. And it's going to spend some time here in minimum velocity state. 2.5 seconds. And then it reached the position of 20. But now it enforced the jerks. And see here is 0.1 for jerk that I specified. And the reason why is that the speed they added, this minimum speed here that you can see low here, does not contribute much. But if the velocity is lower, that the minimum speed is going to contribute, then the jerk is going to be lower. And a lower jerk is better than a higher one. If we would have a higher jerk, we would probably have to compensate for the added velocity for lower speeds. Yes, that was step 1. We can switch this off. And the last one is the jitter suppress time, which you can see now they are kind of nice curves. But the program, when it starts to accelerate or sets a velocity set, when it has to start somewhere, then you are going to get a short jerk or jolt when you start up. And now it's suppressed. But if I set this time to 0 seconds, I register everything. And then we can try to move back to 0, 15. 15, I hit yes, off and on. The reason why it's like that is you could just change the set point here without the program starting. So that's, now you can see you get spikes here. And for the jerks, the spikes are pretty high. And if you look at the maximum acceleration jerks, it's 49. Maximum deceleration jerk is 50. And the acceleration was 0.24. It should be 15 here or something with what is specified here. And the snap, which is the brown one, you pretty much can see that. If we let these spikes pass, of course, it's going to rescale this, so it's going to look at it. So if you just want to record every extremity here or spikes or something, that's just setting that one to 0. You can leave it at 25 milliseconds. 5 milliseconds. It's back. We are done. We could just move back to 15. 8. Move. Oh, there was 14 point. Okay. 14. 8. I'm probably going to get that sooner or later. 14.8 is 0.2 units. If it's doing something. The acceleration was here and the jerk was high. And it landed smoothly at the minimum speed here. And now again here you will probably say, okay, jerk is acceptable, maybe not. We could have forced those. Then we can move to 14.6. Those. Of course, you get a much slower speed. You can't get both ways. You want to contain the jerk, the speed has to be lower, the acceleration is going to follow. Because it's the speed, and of course the snap here is going to be decreased too. And here too, we look at here, we are close to the minimum speed. We could try for 14.5. Even get a lower velocity. Now the velocity is close to 0.01. It's probably something. You can see that was really steep. And now we are really close to the minimum velocity. Let's say 14.42. Now it might not move. Or it might move close to the minimum velocity here. Yeah, it basically moved at minimum velocity. It just entered the minimum velocity state and creep towards that. So if I say I want to move to 14.41 0.01 unit, it's probably not going to move at all. It's not reacting because it's within the tolerance and stuff, and we have safety margins and stuff like that. So I can't move 0.01 unit because that's what I've specified to here. The tolerance 0.001, but then they have these safety margins and stuff that I'm using, so it's not going to move at all. I have to do a little better than that. So 14, I probably. And still I'm just containing the jerk, and I get the acceleration I get is the acceleration I get. The speed I get is the speed I get. And you can see it's not starting to decelerate immediately because the speed determines the jerk that I want to contain. Yes. Now we have pretty much been through these functionality switches. Of course, it could be something else, and this program is fairly general. But what you would do or could do is just to embed it or interface it to another program that implement these speed profiles you might have to use 2 instances of this one if you want to have this added velocity and stuff. You could just embed it and then implement the PLC open speed profiles, maybe in a single function block. Usually they call it instructions, but we are looking at objects here, and a speed drive is an object that is, we are trying to move a real object in kind of a nice speed profile. So it would be a multifunctional function block, which this will be the workhorse doing the positioning, and the wrapper. We just say, okay, we move to, if you do jogging, we set program mode, jogging positive direction, we set program mode 2 or 3, 2 in positive, and a low speed set point, and then we do the jogging, switch off the jogging, jog in the opposite direction, and so on. What it implements is move relative and things like that. And you would we could add a homing procedure to it, that you move to a home position, which is just entering here a set point, move to a home position, or if you have a homing switch, you would have to do it a little differently, because then you would have to run on the homing switch, and then of course you don't know when the homing switch is going to hit you, so you would have to do it a little differently. But you could use this program too. Because what you would do is that you would just estimate, so the homing switch is here, and if I'm doing homing at this speed, I should probably start to decelerate and move at the minimum speed until I hit the homing switch and just stop. So that's what you would do. So this is just a workhorse, let's say a motion profile or program or something like that. Because these instructions that PLC Open specifies, okay, they are instructions, and move absolute, move relative, and so on. And if you look at Siemens, I'm not going to look at it, they have a motion library too with all these instructions, which are basically commands to a drive or to technology function in the CPU. But if you are moving larger objects where it's not a CNC machine that you are controlling, you could use a program like this, and then you would have to have full control with what your object is doing. You don't have to do a lot of programming in, let's say, instructions or whatever. You would have full control in your program. And you could also adopt the program if it has to be changed a little to fit the task at hand. So it would be pretty flexible. So this is basically a class controlling a VSD or frequency converter, moving traverse crane or something that you can. With a powerful CPU, you can run a lot faster than 5 milliseconds, because this algorithm is not time consuming. Let's say in the states, it has a calculation state, but that's not really much to it. But in the other states, the program basically do nothing. So it could run a lot faster than 5 milliseconds. But of course, if you're moving a big object, it's not a 3-axis machine or a CNC machine. It's not going to move fast. Your program doesn't have to execute that frequently either. Pretty much it. That was a demonstration of a program that can control or move an object using a sigmoid speed profiling function. We can have separate jerks or acceleration, deceleration, acceleration jerk, deceleration jerk. This program does not control it according to snap. It would be possible, of course, but the program has been extended to that. But you can contain the jerks if you want to, which is the jolts. And if those are low, the snap tends to be low too. So it depends upon how you want to use it. But still, it's not a complicated program. Doing this math is not complicated either. So to implement that, it's not that complicated.